Hello everyone, my name is Sumit Ghosh and I am from University of Oulu. And the work what I am going to present today is a part of ongoing collaborative work between the Indian Institute of Technology Bombay and then Boku, Austria. So let me first introduce the quenching and partitioning process. So this is this quench and partition steel, well known as a potential candidate, comes under advanced third generation steel. And the key idea behind this kind of processing is to develop martensitic matrix together with written austenite finely divided between this lath martensite structure. And this is the typical way how we follow this quenching and partitioning treatment. So we have to homogenize first at high temperature and then quench down in between the martensite start and martensite finish temperature, and then followed by isothermal holding either at same temperature or slightly elevated temperature for a prolonged duration. And you can see this quench stop temperature and then this partitioning temperature, partitioning time, all these key parameters have significant influence on the final property of the material. So selection of this temperature are crucial, and then alloying impact is also another thing we have to take into account prior to design this kind of processing route. So what happened, during this isothermal holding time, there are several co-current phenomena occurring simultaneously, like austenite decomposition into bainite, carbide formation, and then martensite tempering. So this is not an easy job to control all these phenomena, but through proper alloy design, we can have control the precipitate formation. So in our lab, we have actually designed direct quenching and partitioning process. This is a patented process from University of Oulu. So what we did, we introduced additional thermomechanical control processing. And then instead of doing this isothermal holding, we just did this non-linear holding inside the furnace in order to simulate the industrial coiling simulation. And these are the facility what we have in our lab to control this kind of processing route. Now, coming to the exact processing parameter, what we have chosen for today's presentation. So these are these two typical processing route. One is called direct quenching, where there is no isothermal holding. And another one is direct quenching and partitioning, where there is a long duration partitioning stage together with this thermomechanical control processing, followed by quenching at a specific temperature, followed by partitioning for a prolonged duration. So this temperature has been selected based on the physical simulation which conducted in Gliville simulation. So 150 has been chosen in order to design approximate 80% martensite and 20% written austenite, followed by this 200 partitioning temperature that is quite low. That has been also chosen in order to avoid the unwanted austenite decomposition and carbide formation. And another important thing that we have chosen this medium carbon steel. Why medium carbon? Because our aim is to develop more than 2 gigapascal UTS together with reasonable ductility. So in order to achieve that level, low carbon steel is not enough. And high carbon steel, of course, we could use, but the problem associated with high carbon steel is weldability. So in order to compromise this weldability and strength level, we have chosen this medium carbon steel. Now this silicon is one important alloying element which plays significant role to avoid this carbide formation. So that's why we played with this silicon content. We have this 3 different amount of silicon. So it's varied from 1.5, 0.75, and 0.25. And then we have chosen another additional alloying element, that is niobium addition. So we also wanted to check that how this microalloying element play the role. So these are the microstructural characterizations. So as per this EBSD, you can see it's mainly consisted of martensite together with written austenite finally divided between this martensite lath. But based on EBSD, it's difficult to comment on the exact morphology of the written austenite because of this limitation of the EBSD resolution or step size. But TM can exactly tells you the exact morphology of the written austenite, which you can see these are mostly film-like, and the thickness varies in between 10 to 50 nanometer. Other than this written austenite, we also notice the existence of different type of carbides. For example, in low silicon steel, we have mostly cementite precipitation. Whereas in high silicon steel, we have only transition carbide, that is Fe2C called eta carbide. So what silicon actually playing? Silicon actually preventing or not actually preventing the carbide formation, but it actually delaying the transformation from transition to cementite formation. Now let's have a look on the mechanical property. So as I mentioned, we have chosen 3 different steel with different silicon alloying element and one with niobium addition. So this red one actually showing the with niobium addition steel, and which showed the better UTS together with reasonable ductility. This better UTS maybe comes from this pinning effect of niobium during this recrystallized control rolling. And then in case of low silicon steel, we see the ductility is quite high. So that's maybe due to this formation of bainite. So what happened because of low silicon content? So this carbide form and almost all the carbon taken by this carbide. So there is less amount of carbon present in the martensite. So it's that much of less carbon actually unable to stabilize the written austenite, that causing the austenite decomposition into bainite. So in this low silicon steel, we mostly have the bainite, martensite, and written austenite. Now, we have also conducted the impact toughness test, but clearly we have seen the impact toughness property of direct quench and partition steel improved significantly compared to direct quench variant. Also, we have also checked the mechanical stability of written austenite in different silicon level steel, and then we notice among these 3 variants, high silicon steel showed the high amount of mechanical stability. So next, we also wanted to see that how carbon diffuse from martensite to austenite. So in order to check that, we have conducted atom probe tomography experiment. And here you can see that in case of direct quench specimen, which consists mainly martensitic lath, consists of mainly few clusters which are present inside the martensite. But in case of direct quench and partition condition, we can clearly see the carbon enriched written austenite. And this enrichment is quite high at the interface regime. And inside this bulk regime, it's distributed heterogeneously. And then other than this written austenite, we also notice the existence of different carbides. And we confirmed also the existence of this transition and the cementite based on the stoichiometric ratio. Now coming to the fatigue crack growth and fracture toughness test. So these are the crucial parameters prior to say that this material is good or bad. So we have conducted the fracture toughness analysis of this medium carbon steel and notice there is a significant improvement after this direct quenching and partitioning treatment compared to direct quenching, that indicating that this stabilization of written austenite actually playing the key role. And then when we conducted this delta K control fatigue crack growth, we also noticed there is an improvement in the fatigue crack growth. So the crack propagation is delayed because of the presence of high amount of stabilized written austenite. And how it is delaying? Because there is a strain-induced transformation from austenite to martensite with application of strain. So if the austenite is stabilized enough, so that actually prevents this crack propagation significantly. And that is actually happening. And we confirm this phenomena through this interrupt delta K test. So we interrupt the test and measure the written austenite content. And you can see the written austenite content gradually decreasing with increasing the delta K. So that also further confirm this strain-induced transformation playing the key role for the improvement of this fracture toughness and the fatigue crack propagation rate. And also we varied the different alloying content, and we noticed that there is no big difference in microalloying addition steel versus high silicon, but the difference we notice in case of low silicon. Why? Because as I mentioned that in low silicon steel, mostly the microstructure consisted of bainite, martensite, and written austenite. So these 3 multi-phase combinations actually providing this better fatigue crack growth. And then we also, one more thing I wanted to mention that, for example, here we can see clearly the difference in this Paris regime. But in order to check exactly the threshold, it's important to go beyond. So maybe in DADN values would be in the range of 10 to the power 10 to 10 to the power 11, in that range. And this utilizing this servohydraulic system equipment, it's very difficult or time consuming to go that beyond. Thanks to the ultrasonic facility. So utilizing the ultrasonic, we can utilize 20 kilohertz frequency, and we can conduct the test more efficient way without spending a lot of time. So that's why we have conducted this ultrasonic fatigue test. And this is one condition. So for example, when we compared this direct quench condition, when we did the test in air first, we clearly notice this clear threshold value. And then we wanted to see if there any influence on the air versus vacuum. So we conducted the same condition under vacuum and notice there is a improvement in the fatigue crack growth. So why? Because maybe air actually act as an aggressive environment, so causing this corrosion related stuff. So that's why we see this in vacuum condition, there is an improvement. Further, when we did the additional tempering treatment, we see further improvement. Actually, there are two phenomena may be associated during this tempering. One is dislocation annihilation, that causing the improvement of the fatigue crack propagation. Another one would be the hydrogen, which trapped inside the materials during the processing time. During tempering, maybe some of the hydrogen released out, and that causing this improvement. So we have measured also the hydrogen content within the materials before and after tempering, and we notice there is a slight decrease in the hydrogen content after tempering treatment. That may be somehow corroborating with our assumption. Then we checked also the fracturography analysis, and then we notice in direct quench condition, which has been done under air, clearly we see this intergranular fracture, whereas in vacuum, we see the mixed mode, but after tempering, we clearly see these dimple ruptures. Then we also wanted to check how this ultra-high strength steel behave under very high cycle fatigue regime. So we know this conventional, this fatigue limit, which we say like if there is no failure in between 10 to the power up to 10 to the power 7 cycle, we can consider that as a fatigue limit. That is not valid in ultra-high strength steel, because the ultra-high strength steel are sensitive to the defect. And here what we observed, despite of having 2 gigapascal UTS, these materials are failing at a stress amplitude approximately 800 MPa. And what we notice, almost all the condition, the materials fail from the interior inclusion. And the inclusion size varied in between 15 to 20 micrometer. So despite of having fancy microstructure, if our materials contain this inclusion, it will not help to improve the fatigue property. It will fail at a very low stress amplitude. So in order to investigate the real cause or root associated with this failure, we have investigated the micromechanism based on the TM as investigation. We just lifted out the fifth lamella exactly adjacent to the failure regime. And what we notice that there is a ultrafine grain refinement. So this ultrafine grain refinement, why it is happening? Because there is a tiny crack initiation adjacent to the inclusion, and with progress of the number of cycle, there is the materials experience severe plastic deformation that causing the fragmentation of the martensite into ultrafine grain refinement. Okay, so overall, I'm not going to read, but the overall conclusion is rather than trying fancy microstructure, we should take care the level of inclusion during the casting stage itself. So if we control the inclusion, then this fancy microstructure would help. Otherwise, it's not. By that, I like to thank you for your kind attention, and I like to also convey my sincere gratitude to all this funding agency for providing the funding to conduct my research. Thank you very much for your kindness.